Hi guys. So in this video, I'm going to go over the limit comparison test. In particular, I'm going to go over the limit comparison test for series. This test is used elsewhere as well. For example, there is a limit comparison test for integrals, but the general idea of the proof remains the same, whether you're writing a proof for the limit comparison test for series or the limit comparison test for integrals. The general idea of the proof will remain the same. So let's quickly go over the statement of the theorem. So the theorem says let the summation from n equals 1 to infinity of a sub n and the summation from n equals 1 to infinity of b sub n be any positive series. So this positive series is important. What a positive series is basically, what this implies is that for every natural number n, a sub n and b sub n are both positive. So a sub n and b sub n are always positive real numbers. And then we're assuming that limit as n approaches infinity of a sub n divided by b sub n is equal to L, where L is once again a positive real number. And the theorem says that given all these assumptions, the summation from n equals 1 to infinity of b sub n converges. This is just another way of saying that the summation from n equals 1 to infinity of b sub n will converge if and only if the summation from n equals 1 to infinity of a sub n converges. There is one thing I would like to emphasize. Why is this notation justified? Like, why is it saying that the summation from n equals 1 to infinity of p sub n is less than infinity is sufficient to conclude that this series will converge? Now, in general, this is not true. You can't just say this for any series, but you can say this for positive series. Since b sub n over here is always positive, this series must either converge to a positive number or diverge to infinity. So saying that the summation from n equals 1 to infinity of p sub n is less than infinity implies that it's not equal to infinity, and thus it must converge to a positive real number. But you can't say, I mean, if this wasn't a positive series, then this notation wouldn't have been justified, because while it's possible for the series to diverge to negative infinity or to oscillate somehow and never converge. So anyhow, I probably will make a video about why this notation is justified, because there is a more formal proof for this. Anyhow, so at this point, so the idea is to basically write a proof for this theorem. So at this point, I'd ask you to pause the videos and see if you can write a proof for this on your own. So by now, I hope you've attempted to write a proof on your own. And let's see if your proof matches with mine. There are a couple of ways to prove this. So let's begin. First thing, as I always say, make sure you redefine all your variables. So I'm going to say let the summation from n equals 1 to infinity of a sub n and the summation from n equals 1 to infinity of b sub n be any positive series. And next I'll state all my assumptions. I only have one assumption. I'm assuming, so assume that the limit as n approaches infinity of a sub n divided by b sub n is equal to L, where L is a positive real number. And finally, I want to show that the summation from n equals 1 to infinity of b sub n is less than infinity if and only if the summation from n equals 1 to infinity of a sub n is less than infinity. In other words, one converges if and only if the other converges. Okay, so note limit as n approaches infinity of a sub n divided by b sub n is equal to L, where L is a positive real number, essentially implies, so I'm going to write out the epsilon delta definition for this. So it's for every epsilon greater than 0, there exists a positive natural number, or there exists a natural number n, such that for every natural number greater than that positive natural number. Well, I shouldn't say positive. Natural numbers are always positive. So hold on, let me just move this to the side. And then this means that the absolute value of a sub n divided by b sub n negative L is less than epsilon, which is the same thing as saying, I'm going to just expand this part right here. I'm going to expand this part. So this is the same thing as saying that negative epsilon is less than a sub n divided by b sub n negative L, which is less than epsilon. And this essentially just means that L minus epsilon is less than a sub n divided by b sub n, which is less than L plus epsilon. So this is what I have. And there's one other thing I'm going to do. I'm just going to multiply all of the sides with b sub n. So I'm going to get L minus epsilon times b sub n is less than a sub n, which is less than b sub n times L plus epsilon. So b sub n or L plus epsilon times b sub n. So this is what I have, and essentially this is the part that I'm going to use in order to write a proof. So first thing I know is that this entire condition is true for any epsilon. So it's true for every epsilon, thus it must also be true for the epsilon of my choice. So I'm going to say let epsilon be any real number. Well, instead of saying this, I'm going to say I pick an epsilon such that 0 is less than epsilon, which is less than L. So basically what I'm going to do is I'm going to pick an epsilon that lies between 0 and L. Then there must exist some positive natural number n, then there must exist some natural number n naught, such that for every natural number that's greater than this natural number, so if n is greater than or equal to n naught, I must have that L minus epsilon times b sub n is less than a sub n, which is less than L plus epsilon times b sub n. And now here's the idea, let n naught, and I'm going to say that this is condition number 1, let n naught be, or take n naught to be, take n naught in n such that 1 is satisfied. So I'm basically just going to pick any natural number that satisfies condition number 1, and I know that there has to exist such a natural number because of this condition. Because we know that this statement has to be true, so it has to be true for some natural number. So let's just say that that natural number is n naught. And then I'm going to say let n be a natural number, and I'm going to assume that n is greater than or equal to n naught, because I can assume that over here. Then I get that L minus epsilon times b sub n has to be less than a sub n, which has to be less than L plus epsilon times b sub n. And just for the sake of simplicity, I'm going to call small m to be equal to L minus epsilon and capital M to be equal to L plus epsilon. So there you go. And then I'm going to rewrite this condition. So if I just substitute everything back in, I'm going to get m times b sub n is less than a sub n, which is less than capital M times b sub n. And I know that this that 0 is less than all of these numbers because of my choice of epsilon. So when I picked epsilon over here, I made sure that epsilon was less than L, and therefore L minus epsilon has to be greater than 0, and thus m has to be greater than 0. And since b sub n was already positive, m times b sub n must also be greater than 0, which is why I have this condition over here. Okay, and now what I'm going to do is I'm basically now done. Now I just have to apply the basic comparison test over here. Finally, So there are two cases now, because remember, I have to prove that if the summation from n equals 1 to infinity of b sub n converges, then the summation from n equals 1 to infinity of a sub n converges, and then the other way around. If the summation from n equals 1 to infinity of a sub n converges, then the summation from n equals 1 to infinity of b sub n will also converge. So first thing, the first case number 1 that I'm going to show is that if the summation from n equals 1 to infinity of b sub n converges, then the summation from n equals 1 to infinity of a sub n will also converge. So let's go. I'm going to assume that the summation from n equals 1 to infinity of b sub n converges. Then, by the basic comparison test, so by the BCT, as the summation from n equals 1 to infinity of b sub n converges, and because for every natural number n, if n is greater than or equal to n naught, then this condition is true. So I don't need this m times b sub n for now. I'm just going to keep the remaining part. 0 is less than a sub n, which is less than capital M times b sub n. I know that the summation from n equals n naught to infinity of a sub n must also converge. This just follows from the basic comparison test. Then, as the convergence of a series depends only upon the convergence of its tail, and because we know the tail converges because, well, the summation from n equals n naught to infinity of a sub n converges, we can conclude that the summation from n equals 1 to infinity of a sub n must also converge, and that completes first part of the proof. So just to give you a little bit of an emphasis about what's happening over here, the first thing I did is I applied the basic comparison test. And through the basic comparison test, basically the idea is, if I know that this is true, if 0 is less than a sub n, which is less than c times b sub n, and I know that b sub n converges, then from the basic comparison test, I can also conclude that b sub n converges. However, the issue was that this inequality over here is only true after some natural number n, after some cutoff. So that cutoff might be 5. I mean, this inequality might be true for every natural number greater than 5, greater than 6, which is why by using the basic comparison test, I was only able to conclude that the summation from n equals n naught to infinity of a sub n converges. But that is not that big of an issue, because the convergence of a series will only depend upon the convergence of its tail. And what I mean by that is that we do not care about the sum of the first finitely many terms. So in this case, for example, the only thing that's left, or the difference between this this series and this series, is basically that the summation from n equals 1 to infinity of a sub n is equal to the summation from n equals 1 to n naught minus 1 of a sub n plus the summation from n equals n naught to infinity of a sub n. Now note that this is always a real number. This is always a finite real number, because you're computing this sum up to a finite natural number. And since this is always a real number, what I can conclude is that if this converges, so if the summation from n equals n naught to infinity of a sub n converges, then the summation from n equals 1 to infinity of a sub n must also converge. So that's basically the idea. When I say that the summation, this is basically the idea behind, that the convergence of a series is only dependent upon the convergence of its tail. You can ignore the first finitely many terms. But that's the first part of the proof. There's a case 2, which is pretty similar. So case 2 is about proving if the summation from n equals 1 to infinity of a sub n converges, then the summation from n equals 1 to infinity of p sub n must also converge. So once again, I'm going to assume that the summation from n equals 1 to infinity of a sub n converges. Okay, and I'm gonna apply the basic comparison test again. Then, by the basic comparison test, as the summation from n equals 1 to infinity of a sub n converges, and because for every positive natural number n, if n is greater than or equal to n naught, then, now in this case, I'm going to ignore this capital M times b sub n. I am only concerned with this part. So as 0 is less than small m times b sub n, which is less than a sub n, the summation from n equals n naught to infinity of p sub n must also converge. And this allows me to, once again, I'm going to use the same reasoning. So I'm going to say then, as the convergence of a series depends only upon the convergence of its tail, and because the summation from n equals n naught to infinity of p sub n converges, we know that the summation from n equals 1 to infinity of p sub n must also converge. And that completes the proof. So I've proven the inequality both ways. I've proven that if the summation from n equals 1 to infinity of b sub n converges, then the summation from n equals 1 to infinity of a sub n will converge. And if the summation from n equals 1 to infinity converges, then the summation from n equals 1 to infinity of b sub n will also converge. And that are both the parts of the proof. They are quite similar. There are just two things that you need to know to be able to write this proof, or to be able to complete the final part of this proof. The first thing is the basic comparison test, and then the second part is this idea that the convergence of a series depends only upon the convergence of its tail. This first part over here, this was also important because, of course, in order to obtain this inequality over here, this inequality which we used in order to apply the basic comparison test, you need to know the epsilon delta definition of what does it mean for a limit as n what it means for a limit to approach infinity. So the epsilon delta definition is also quite important. But if you know the epsilon delta definition, if you know what the basic comparison test is, and if you know the theorem that the convergence of a series depends only upon the convergence of its tail, then this proof becomes quite trivial. There is one thing though, this what I've shown you right here, it is the limit comparison test, but there is also an extended version of the limit comparison test. And the proof for that is actually quite similar. So I'm not gonna show that proof, but I will tell you what the extended limit comparison test is. And maybe you can see if you can do that on your own. I'm not going to tell you what the conclusion is either, but I'm going to tell you that the extended limit comparison test essentially comes from the idea that what happens if the limit as n approaches infinity of a sub n divided by b sub n is 0, it's 0, or limit as n approaches infinity of a sub n divided by b sub n is infinity. So in either one of these cases, you can actually make a conclusion. You can say something about a sub n, about the summation from n equals 1 to infinity of a sub n, and the summation from n equals 1 to infinity by b sub n. So see if you can figure out what that conclusion is. It is not as strong as this one, but you still get some conclusion. You can still make a conclusion. And once you know what the conclusion is, see if you can write a proof for it. And whatever the conclusion, whatever you think is the conclusion, just leave that down in the comments below. If you have a valid proof for it, just state what the general idea of the proof is, and I'll let you know if your conclusion and if your general idea for the proof is correct. And yep, that's pretty much it. That was the limit comparison test. I hope you enjoyed the video, and yep, I'll see you in the next video.